Okay, so it's 5 minutes past 10. I think I'll start, and I just thought I'd share my video at the start, so I'm not just a total disembodied voice all the way through. I take it everyone can hear me okay, and they can see the first slide of the presentation. If you can't, just shout out or post a message in the chat. But I'm not hearing any notification sound, so I assume everything is okay. So this is the advanced topics part of the GPU programming using OpenMP course, and I work at EPCC and I have some experience of using OpenMP offload. I used it recently running a geoscience code. So it's a geoscience code that takes measurements of the magnetic field that are scattered across the globe. It's not a uniform coverage, but from those it can work out a uniform vectorized magnetic field of the Earth's crust at quite a high resolution. And that code was a Fortran code, and it was very amenable to offloading various heavily used loops off to the GPUs. And it worked quite well using the NVIDIA Fortran compiler. So I just thought I'd give a bit of a bio of my relevant expertise, and I'll just now stop sharing my video and continue with the talk. So we're going to cover a number of areas. We're going to look at OpenMP and ROCm interoperability. So ROCm is AMD's suite of software for allowing you that enables you to use their GPUs. So it will include things like compilers and debuggers and profilers, as well as libraries for doing operations that are typical to science code, so linear algebra stuff, fast Fourier transforms, things like that. And ROCm also has inside it its programming model known as HIP. So yeah, we'll talk about that, how you can integrate that with OpenMP directives, and then I'll talk about data mappers and how you can map heterogeneous data types to the GPU. We talk about the types of memory that are in play when you're programming for GPUs on the host, and a little bit on the GPU itself. Talk about how you can control the allocation of that memory, and how you may want to specify how the data is going to be organized within memory and how you're going to control access to that. And then lastly, I'll finish off with a discussion about asynchronous tasks. You can send instructions to the GPU, but not block on the sending of those tasks, leaving you free on the host to do other work. So so ROCm is AMD's equivalent of NVIDIA's SDK. And ROCm provides their programming model, their library called HIP, which you will call functions from this library to allocate memory on the host, or sorry, to allocate memory on the GPU and to move data from the host to the GPU. And you can also use it to launch kernels and things like that. So HIP is AMD's programming model, and it's equivalent pretty much to what NVIDIA do in their programming model, which is called CUDA. So you'll see on the slides that I'll refer to both of those in certain places. When you say if you had some code that you wanted to offload to GPU and it was doing some computationally expensive parts, maybe a particular fast Fourier transform or some linear algebra operation, and you think, well, I don't want to just re-implement this on the GPU, I can use the functions that are already provided for me from a vendor library that either NVIDIA or AMD have provided. Now, the parameters to the library function may expect pointers, and so you'll need to, if you're using that within an OpenMP offloaded region, you'll need to indicate that that pointer already exists, is pointing to data that exists on the GPU. And so here we're just preparing to show you some code example of this. You may have a variable that instead has already been mapped, say, it's a different situation. And when you're now calling the hip or CUDA routine, well, if you're using those programming models, you want to avoid reallocating the data on the device or transferring it from the host to the GPU. So here's an example of what I mean. You would specify alongside your OMP target construct, you would have a little macro here called use_device_address, which tells OpenMP that var_a has already been mapped to the GPU. So otherwise, going into this target region, OpenMP might generate code to do the mapping of the data that it thinks, well, is on the host, and that would be unnecessary if it's already on the GPU. So here's a bit more of an involved example. So this is when you're actually calling a routine from the ROC linear algebra library, ROC-BLAS, and it's just a matrix multiplication here that's going on. So we have a target construct and an outer target construct where we're actually mapping our data. We've got 3 arrays, A, B, and C, and we're mapping those into the device. But now when we come to actually call the ROC-BLAS dgem operation or the function, we want to make it clear to the OpenMP runtime that these arrays that we're passing in, these are pointers, and they're already pointing to data that's on the device. So it could be, this is a very condensed example, but you could be in a situation where in between the 2 target constructs, there is lots of code. So you could easily miss that those arrays have already been mapped. So what's going on, just to be clear, is that we're multiplying the A and the B arrays, and then we're adding C. And then the result is returned in C. So there's a Fortran example of this doing exactly the same thing, and it's been a little bit clearer about the descriptors that are associated with each of the mappings of the array. So you can see the C has the from, so prefix. So the result is coming back in the C array. Now it could be also, I should say, that the outer target construct may exist in a different compilation unit to the inner one, so a different source file. So it's just allowing you to specify to the inner target region that, hold on, this data here that I'm providing to you already exists on the GPU. Now, you may, using the HIP or the CUDA programming model, you start off allocating memory on the device using a routine that you call from the host. And that's preparatory to maybe doing a data transfer. Again, you can do that using a HIP call. But you need to be aware of, if you're using OpenMP and you're not just doing straight HIP code, there's something that you would need to do to make it clear to your OpenMP runtime what is actually going on. So here now we use a slightly different clause. It's kind of same thing, the is device pointer, to tell OpenMP when certain pointers are pointing to data already available on the device. So this is something that you would do when you're actually explicitly making HIP calls to allocate the data on your GPU, and that's what's going on here. So we're allocating double arrays of size n called B_device, C_device. And now we go into our OpenMP target region, and we're making it clear to OpenMP that C_device and B_device have already been allocated, and they already exist on the GPU. Now, just to condense the example, there's a bit of code obviously that's been missed out where we initialize B_device, but in the actual loop that we're parallelizing here, we're just transferring the values in the B array to what's in the C array. If you were to just run this without the teams distribute, basically all the iterations in this loop would be run by one thread running on one compute unit. But because we have the teams distribute, then those iterations, maybe there are thousands of them, but those iterations are distributed across the GPU threads that are running across the compute units that exist on the GPU. So that's a C example. Fortran example is just a little bit more involved because your HIP malloc routine is expecting a C pointer. So that's the type of pointer you have to use. But when you're going into the rest of your code and you're going into your Fortran OpenMP region, it expects a Fortran pointer to be there. So we have to do a bit extra in our Fortran code example. We have to convert the C pointer to a Fortran pointer. But again, we use the is_device pointer with our Fortran pointers to tell the OpenMP that these already are pointing to data that exists on the GPU. So how a Fortran pointer is different is that it's not just pointing to the data in the array, but it's pointing to metadata about your data type. So such things as the rank of the array, how many dimensions does it have, and the size of each dimension, and so on. So that's the end of that section about how to mix calls to HIP routines with OpenMP offload. Does anyone have any questions about that part? Yeah, there's a question from Monish. Well,
so if I'm getting it right, the parallelism comes into play when you are using OpenMP.
Yes, that's right. So at that point, you're using the team's distribute keywords alongside the OMP target construct. And what you're saying is whatever, say it's a loop, those iterations now can be assigned to the various GPU threads running across the compute units on the GPU. So I explain a bit more in later on, but just to prepare the way, in OpenMP terminology, you have this concept of a team. So a team is maybe like the subset of the iterations within a loop. And that team will be assigned to a particular compute unit that's on the GPU. And then those iterations will be then further divided amongst the GPU threads that can run in parallel on that compute unit. And on a GPU, you'd have typically 100 or so compute units. Does that answer your question?
Yeah, that answers my question. So one more follow-up is, can't the CUDA or IP does this stand alone without the OpenMP?
So the CUDA, the programming API, is separate to OpenMP. But it doesn't, within the specification, it doesn't talk about OpenMP. But if you're using OpenMP alongside calls to CUDA, such as you've just seen when you're allocating memory using a CUDA call to allocate memory on the GPU, then you need to take certain steps. You need to use certain macros to make it clear to the OpenMP region where your data is. It actually is on the GPU, for example. Okay.
That answers my question. Thank you.
Okay, thank you. Okay, if everyone else is okay, then I'll move on to the next part of the talk about custom data mappers. So you would have seen already, I think, examples where you map data to the GPU, and those examples would have involved base types. So it would maybe have been an array of integers or array of doubles, something like that. But you may want to have more complex types in your computation, and by complex I mean something like a composite type, so a structure. So you have a structure and you have various fields that in there that are made up of base type themselves. So here in the example we have my_struct that has pointers to 3 array of doubles, and each array is of size n. So this would involve quite a bit of work where it would add extra code when you're going into a target region to map all of those fields individually. I'll just explain what I mean. So you'd have to have something like this. So for the C example, you can see you get into your target region, you do a map, and you map the the actual instance of your my underscore struct, A there, so to get the size, the N field, but then you'd have to do the actual arrays explicitly. So that's the C and the D and the E array. And you'd have to do that every time you're going into a target region, and for every variable, for every instance of your my underscore struct type. And you see it's very similar for the Fortran as well. It just uses a different symbol to indicate the start of a field name, a percent sign, rather than a period. But you can wrap all of that up, all those mappings of the individual fields in your structure. You can declare a mapper, your custom mapper, and you can specify that this is going to work for a particular type, my underscore struct, and then you can give it a dummy argument, X, and then what you've just seen on the previous slide, you can do once only when you define your custom mapper, and that's what's happening here. So we're using an OpenMP declare mapper construct, and then we're making sure that when we need to map an instance of that type, everything is being written to the GPU. So that's the size, the N value, and all of the arrays too. So you just define that once, and then subsequently in your code, whenever you need to map instances of my underscore struct, it's very simple. It's as simple as if you were doing a base type. And in fact, it's a bit simpler, you could say, because if you're doing a base type, an array of a base type, you would still have to have the dimension sizes in there, but that's all being put into the custom mapper that you've defined at the top. So it makes your code cleaner, easy to read and easy to understand, especially if you come back to it after a certain amount of time. So that's quite a useful thing to do. So that's it. That's a bit of a short section. I take it that was clear to everyone. Does anyone have any questions about that? No? I'll just move on then. So now we're talking about the various types of memory that we can use on the. Oh, there's a question from someone. Do the custom mappers have to be in the same file as the map statements, or could they be defined well? I think it may depend on the compiler with this, but it would certainly be more convenient if they were. I think. I don't see why not. Why it can't be. So it could certainly be at the top of the source file. But you'll see later on. I mean, there's other constructs that we can have. Say if you wanted to map data, and you're using an enter data clause, and you would have an exit data clause. They could exist in one compilation unit, one source file, and then the code within can call functions from other source files, and they could call other routines, which you then call a loop, which you then offload. And you offload, and that's using data that's previously been mapped in the enter data structure. So taking that example, I know that can work for that situation. I would expect it could work for a custom data mapper too. So yes, I would say. I'll double check though after the talk. Okay, thanks, Ian. So we're going to talk about the types of memory that come into play when you're programming for the GPU. So on the host, you have pageable memory, and that means when you do an allocate statement, you're giving an address that refers to a virtual address space. And that makes things very convenient for the programmer, for the person writing the code, because they're always working in terms of this virtual address space. and actually the details of where your data exists on the memory hardware on the system on which you happen to be run are handled by the host operating system. Now, the GPU won't know about the fact that there's a potential for the operating system may move the data within the memory hardware due to system load and so on. So to allow for that, you can have this concept of pinned memory. So that means that the data that's allocated in a certain part of the memory on the host stays there so that it's safe to then transfer later onto the GPU. Now, for the latest generations of GPU hardware, they will have a concept of unified memory, which means that you don't have to explicitly map data from host memory to device memory. If it's in unified memory, then both host in theory and the GPU, the code on the device, can see it and just access it in the usual way. Unified memory can be implemented in software, meaning that that work is being done behind the scenes to check where memory is when it's referenced, and if it's on the host, it will then, under the hood, make sure that it's being mapped. But also, you have unified memory in hardware. So, and that makes things quite convenient for the programmer in that you have to remove the explicit code that would otherwise be needed to handle the mapping of data from host to device. So here's a schematic of what's going on with pageable memory. So on a host system, you will have memory that will be organized in terms of DIMM strips, and your host may be managing many tasks that are occurring at once, and it may be swapping between them, and so there may be a need sometimes to move a page of memory that's being allocated from one part of the memory hardware to another. It's convenient having this virtual address space. Makes your code more portable. You can move it to run on different machines, and also your virtual address space can be larger than naturally physical memory. But it not only could your block of data that resides in virtual memory be moved from one part of the memory hardware on the host to another, but it may be actually swapped out to the hard disk as well. If there's, if your particular process has been inactive for a while and there are other processes that are now going to be scheduled to run on the host. So this is, I've just kind of explained this already in this text, so I'll just move on. Now, for pinned memory, whenever you map data to the GPU, so you've already got data that's been allocated, you've got memory that's been allocated on the host and data has been stored in there. When you then want to do a map, there's a potential for 3 operations that would then need to run. First of all, you need to allocate pinned memory of the same size as what exists in pageable. And the second operation, you need to move the data from the pageable to the pinned memory. Then only then are you ready for the third operation, which is the actual transferal of data from pinned memory to memory on the GPU, usually the global memory on the device. So that would be a pain if you had many offloaded loops within your code, and each time you were having to map data, and every time you are mapping arrays, you're having to go through those 3 operations all the time. So you could instead declare your arrays that need to be offloaded. You could declare them as pinned, and because they are pinned, they will automatically, the memory needed for them will be allocated in the pinned memory on the host, so which means that the host isn't going to move them around, isn't going to swap them out to the hard disk or move them to another part of the memory hardware, so they remain fixed. And then when you come to a mapping to offload that data, you're only doing the one operation. So the OpenMP runtime knows that it's already in pin memory and can just get ahead with transferring that data across, knowing that the host operating system isn't going to come in at some random point in time and maybe move that data to another part of the host memory. So that pin memory basically does work up front for you to make your mappings more efficient later on. So I've just explained that, what's there in the text. Nowadays, this idea of non-unified memory. So you have this memory hierarchy essentially on the host, and you have a similar kind of thing on the device. So you have random access memory on the host typically. You have high bandwidth memory on your GPU. I think on the MI210s you have 64 gigabytes of memory, but you can have as much as 200 for the latest devices available. But it's the same kind of thing. You kind of have a virtual address space on both platforms. Now, for unified memory, this can be implemented in software. And so you may have a situation where a device needs to access your array, called A in this case, but actually at the point of first accessing it, it actually exists on random access memory, which is on the host. So when this happens, the OpenMP runtime will be hitting a layer underneath it, which is provided by the NVIDIA SDK, maybe part of the CUDA environment. But what that's doing is it will recognize that actually that data exists on the host, and then in the background it will do an implicit mapping of that data so that it is now moved to the GPU device. And so then from your perspective of the programmer, you don't need to explicitly map that data. That will be done for you at runtime. And to specify that you're using unified memory, you can have an OpenMP directive at the top of your source file, requires unified shared memory. And that means that memory allocated is going to be in the unified memory. And if you're using our later version of the very latest versions of a GPU, so for AMD, something like the MI300A, or for NVIDIA, the Grace Hopper H200, there's actual memory that is in hardware is unified. So it makes things more efficient because you're not needing time to map data from the host to the GPU. And also as a programmer, as developing your code, you can get on with actually what's the computation that's taking place on the GPU. You're not having to add extra code to do the mapping to and from. So yes, just here's a bit more information about how the memory is organized on the device. So I talked about that the parallel processing that can take place on a GPU is grouped in terms of compute units, and each compute unit will be made up of a number of SIMD processors that can support a number of threads running in parallel, but each of these compute units have their own local data store or shared memory. And it's not particularly big. You're talking in terms of kilobytes. There may be a cache too in between the local data store and the global memory, which may be a bit larger. That may be in terms of megabytes, but the global memory itself, which could be seen by all the threads running on all the different compute units, that's of the order of gigabytes. So the closer you are to the GPU thread, the faster the memory will be, but the smaller the memory capacity will be compared to the global memory. Yeah, so here's just a summary of what I've just said. We'll go into more detail about GPU memory when we get on to the performance talk that comes after this. So does anyone have any questions about this part? I think that's the last slide. No, okay, I'll move on to OpenMP memory allocators. So these allocators have two concepts. They have a concept of a memory space, and then a series or a number of allocated traits. So, and these, I'm talking about OpenMP allocators here. So when you have something like OMP default memspace, you're just saying to the runtime, just choose whatever memory space is convenient. But to give you an idea, so the sorts of mem spaces that you may want to define, well, not define, sorry, but are available. There are memory spaces to indicate that you want something that has a large capacity. You could say, I want a const mem space, so that's going to hold data that's, once it's there, is not going to change. You might want a memory space that has a high bandwidth or one that has a low latency. So those are different types of memory space that you may be able to use. Now, these are memory spaces that are defined in the OpenMP standard, but you would need to check whether or not they are supported by the compiler that you're using. So you would need to read the compiler manual just to be sure. Now, allocated traits are things to do with how the raw data is organized within memory. And then you can also basically say how, which processes will access that memory. You can specify access control. So here are the sort of allocated traits you might define. You may you would define an alignment for your data. So what you're saying is there that basically memory is organized, or data within memory is organized such that it falls within word boundaries, where a word might be 4 bytes or 8 bytes. So you can organize your data so that individual data items or elements in an array take up a fixed number of words. So that when you then do a memory load operation and you're reading in a fixed number of words, you know that you've read in one data item. You don't get a situation where you've done a memory load and you basically read in part of one element from an array, and then you need to do another memory load to get the rest of it, and then you would need to go and combine those two halves or those two parts to make up the whole element that you can then use it for computation. So by doing alignment, you would be padding the data that you have such that it fits the word boundaries. So you're allocating more memory in effect, but the subsequent memory accesses will be more efficient because the code would know exactly how many data items are going to be read by a certain number of memory loads. And then as regards access, you can specify that all the threads running on the GPU can access the data that's been allocated, or you can say it's private to a particular thread running on a particular compute unit, or you can say it's going to be shared, this data is going to be shared by all the threads that have been assigned to a particular team. So those are all the threads that are running on the particular compute unit. So this maybe then would be data that would exist in the local data store. You can maybe go to a finer grain of control than that, so you can have C groups. So you'd have a subset of threads that are running as part of one team, and they may be working on some piece of work, and there needs to be some synchronization. Maybe there's a mutex variable involved, so a thread within that group takes control once it has ownership of that mutex. I think that's kind of less likely to be a reason to use that, because generally your threads running within a team are all doing the same thing and they're all working independently, because that gives you good performance. That means that you're doing computation all the time on your GPU. And the way that these things are implemented, the support is variable across compilers. And finally, you can have pin memory. You can indicate that as well. So this will be something for memory there that applies to running on that's been allocated on the host. And so all of this, I think I mentioned at the start, you could use this for memory that's allocated on the device, but it also applies to memory allocated on the host. So here's a code example of how you would set this up. So you've got an example using C and then an example using Fortran. So they're just equivalent snippets of code here. So you're declaring a namespace, and you're saying you're assigning the value default namespace, but you're free to use other things. You could go for a high bandwidth memory space if you wanted to, and then you specify an array, which is a list of traits. So you've got a list of tuples effectively, where you identify the trait you're interested in, and then you give the value that you want to set that trait to. So here we're aligning on 128 byte boundaries. And then below here, you define what is in effect a custom allocator. So you use the OMP init allocator method, and then you're passing your memory space, and then your array of traits comes in there. So all of that is how you define your particular allocator. So these are basically hints to the compiler. It is not guaranteed what will happen when it comes to run. And when you probably didn't quite mention this, when you actually come to use your custom allocator, you use this colon syntax, and the item list are the list of variables that are going to be allocated according to the traits in the memory space that you defined in your custom allocator. Because of this variable support across compilers, it's a good idea to run your compilation in verbose mode to get more information about what's going on and what's happened under the hood, and also make sure you read the compiler manuals for this particular area of how it supports OpenMP allocators. So here's an example of doing a memory allocation on the host. It's very straightforward. We've defined our my_alloc custom allocator, and we're saying we're going to allocate B according to whatever is specified in that allocator. Now, actually, for using custom allocators for allocations taking place on the device, it's a little bit cumbersome, but I'll just go through it. So you have your OpenMP target region. You've got your users allocators. So you're saying to the OpenMP that I'm going to use a particular allocator here. And you might have a list of them actually. So we've just got one in this example, my_allocator. And then you have a map clause. You're not actually transferring data from the host to the device, but you're saying here that there's going to be an allocation of memory on the device. And then you have to have this allocate word here, a function, and then you pass it again, your custom allocator with the colon, and then the list of variables that are going to be allocated in that way specified by my_allocator. So the letters ALLOC occur about 5 times here. So that is just a little bit cumbersome, but especially compared to when you use custom allocators for memory on the host. But that's the way it is. That's the way it's defined in the OpenMP standard. So OpenMP doesn't yet, or maybe I'm not sure it ever will be, provide a mechanism for allocating data within specific memory areas on the GPU. So for example, on the local data store, the kilobytes of memory that you would have per compute unit. But you can structure your code within an OpenMP offload region that effectively provide hints to the compiler that that is what you would want to do. Now I say I don't think that there will be an explicit mechanism, because one of the advantages of OpenMP offload is that it's hardware agnostic. When you write your code, it should in theory work on an AMD GPU just as well as it would work on an NVIDIA GPU. You might have to use a different compiler. You may have to go to an AMD specific compiler in the first case, and then an NVIDIA one in the second. You may be able to get away with using a GNU compiler, so a GCC compiler that provides offload capability. But the point is, you have this hardware agnostic approach with OpenMP. And if you got into things, if OpenMP changed such that they've got to be explicit, like you're going to be able to use a local data store, you're making assumptions about the hardware, that it provides such memory, for example, and so you're kind of maybe introducing a restriction that your OpenMP code could then only run on certain GPU hardware. But maybe not. I'm not sure if this will be a way that OpenMP will change in the future. So here's the kind of thing about what I mean about providing hints that memory is going to be allocated on the local data store. So we've got our target teams construct here, and we're specifying 4 teams. So we're looking at using 4 compute units on the GPU, and within our offloaded region, we've declared already a C array of block size, and so that could be, because we've got 4 teams, that could be split into quarters, and then each quarter is written to the local data store on the team. And so that when the threads that are running within that team, they all have access to the data that they need. So that may happen, it may not. You can again do the compilation of verbose mode to see any indication there, or afterwards we actually run code to profile what's going on. To use one of the profilers that are provided by the GPU vendors. You have RockProf for AMD, or you have NVIDIA Insight Systems. And so the Fortran example is much the same. You've just got a bit of difference there in that within the target teams, you're calling a subroutine that's actually then parallelizing that loop across the various threads running within the 4 teams. So here's how you may do something a bit more explicit, in that you can use a particular allocator called OMP pteam mem alloc. So now we've got our target teams, and we've actually defined our C array outside of the OMP construct, and we saying that we're using this particular allocator that's provided for us by OpenMP, and then we're going to allocate that C array explicitly on the device and using the pteam mem alloc allocator. And again, that's another way of indicating that you want to use the memory that is closest to the compute unit. So that's the end of that section with memory allocators and how to specify memory spaces and memory and access traits and the like. Does anyone have any questions about that section? Fine. Okay, that's good. I'll get on with the last part now, the asynchronous offloading. Now, by default, when you're using OpenMP and you're mapping some data to the device, or you're launching a kernel, or you're getting data back from the device onto the host, those 3 kinds of class of operations, they are blocking. So you can't get to the kernel launch until you've mapped the data. But it's possible to add a no wait clause to your target construct definition, and to say that the mapping of data, your host isn't going to block on the mapping and is free to do other work. And when the CPU has done that work, it can then it wants to check in and see whether the work that it's scheduled to run on the GPU is completed, and then you can do a task wait. You can also, if you've got lots of different pieces of work that you're offloading to the GPU, and there happen to be dependency between them, you can also specify that, so you don't end up with one piece of work running on the GPU before a preparatory work that needs to be done has taken place. So this is an example of when you're mapping 2 arrays to the device, XSI and YSI of size M. And you're going to go into that mapping, but you can specify no wait, which means control passes immediately back to the host, and then you're free to do whatever computation. There may be some computation that you need to do on the host. Maybe you need to prepare the data for the next kernel that you are going to launch. And But if you're are going to get to a point where you are ready to launch that kernel, so by kernel I mean a discrete body of computation that takes place on the GPU and is normally partitioned and assigned to the various compute units. So once you've done the host computation, you do a task, and you may do that because the host is then getting ready to launch the kernel that requires XSI and the YSI arrays. That's quite a straightforward thing to do, and it means that the latency associated with mapping data from the host to the device is hidden in one respect, because you're not being blocked. The host is still doing useful work, so you're improving the performance of your code. So here's how you might do a target teams to overlap computation more explicitly. So for the C example, you can see you've got your target teams distribute parallel clause, which is immediately before a for loop, and it's that loop called computation A that's going to be offloaded, and you're doing a no wait, and you go. Therefore, the host is now iterating through a loop B, but those iterations are being done on the host. So it's just an example of the sort of computation, how you would code the computation that takes place on the host, while computation on the device is also taking place. Now you could run multiple kernels at the same time using the no wait clause. So you just have to be aware of how many compute units those kernels would need to run over, and you need to make sure that you have enough compute units on the GPU to be certain that different kernels can run at the same time. And you would probably want to profile your code, just double check that those kernels are indeed running in parallel. So here's another example of doing separate kernels running on the device. So it's the same as the last one, but now computation A, as before, that was running on the device with a no wait clause. We go immediately into computation B, which, because we have the target teams distribute pragma directive immediately before that loop body, that's also going to go on the device too. So in effect, we're running two kernels, and the only thing that may prevent that from happening if M was too big, if the body of those loops was doing too much computation, but actually there weren't any spare compute units to do the B loop. You can see the C and the Fortran examples are very, very similar. Now we can specify dependencies in order to make sure that the pieces of work that we're offloading to the GPU happen in the right order. We have three types of dependencies. We have an out dependency. So if you are mapping an array, say array X, and you say there's an outward dependency, meaning that there's going to be another piece of work that's going to be scheduled or offloaded to the GPU that will need this data X to be in place on the GPU before it can run. And so there will be, for every out dependency, there's a corresponding in dependency on, say, the kernel launch, for example, that requires X. So that will say I have an independency. Maybe if you're having kernels that are running in some kind of pipeline, and so you have a kernel in the middle on a particular variable, that way would have then an in and an out dependency, an in on the kernel that's executing before, and an out on the kernel that's going to execute after. So here's just a toy example that just shows you the syntax for using these three types of dependencies. So we've got an outward dependence on a mapping of X, and then the kernel that subsequently runs, you're saying that there's an input dependence on that, and also there's an output dependence for the next kernel that's going to run. And for the final kernel, we just have the in dependence. Now, this is a toy example which is just illustrating the syntax. It makes no sense to run this because effectively you're using the no wait clause to do non-blocking operation, but the dependencies are forcing you to run these three things in serially, one after the other. But it's just to illustrate the syntax here. You would maybe that you would have many kernels that you're wanting to launch, and there aren't dependencies, or maybe you're only dependent on one array of the arrays that are needed for the kernel input parameters. Yeah, so these are the sorts of things you can do to make sure that the work you're scheduling on the GPU does run at the right time. And the Fortran example is very, very similar here. So just to summarize this talk, we talked about OpenMP and your offload and how you would make that work if you're also doing calls to the ROCm HIP library, or might be the NVIDIA CUDA library. And then we talked about data mappers and the types of memory that are in play on the host and on the device, how you would allocate memory with such that it's compatible with OpenMP for the host and the device also. And then lastly, we just talked about asynchronous tasks. Does anyone have any questions about the last section, or maybe the talk more generally? I think if not, what I can do, shall we take a 10-minute break? Is that okay for everyone? So I'll start again on the next talk, which is about performance, at about 5 minutes past 11. Is that okay for everyone? If you just say yes in the chat, or yeah. Okay. So one person, I take that as being the spokesperson for the entire audience. Yeah, okay, I'll see you again. I'll start up again at 5 minutes past 11. Okay, everyone. I'm going to start the presentation of the next set of slides, talking about performance optimization. So going to cover a number of areas. We're going to talk about occupancy. So that is how well the work you're offloading, how good a use are you making of all of the compute units that are available on the GPU. Then I'm going to talk about branching, and how that is bad for GPU performance. And then I have some discussion, talk about memory optimizations, or how you can organize your data within memory so that you're reducing the amount of time needed to take data from where it actually is to where it's needed. And then lastly, just a few miscellaneous topics at the end that didn't fit in any of the previous topics. So throughout these slides, I will use numbers that are relevant for the AMD MI210 GPUs that we have on ARCHER2, but you have numbers that describe the same concepts for other GPUs. So just bear that in mind. So onto occupancy. So GPUs are high latency, high bandwidth devices. If you've got all of the GPU threads running on all of the GPU cores across the compute units, then you're getting data in parallel and computing on that data, so you're achieving good bandwidth. But when you're doing a single transfer of data between the different levels of memory on the GPU or from the host, there is a high latency cost with that. So we often talk about overlapping compute with moving data around in order to hide the latency costs associated with that data movement. Obviously, you need to have enough tasks to fill your GPU and the compute units that are on there. You don't want to have compute units that are idle. Now, the AMD MI210, that has 104 compute units, and each compute unit has 4 SIMD processors with 16 lanes. So one SIMD processor, and 16 lanes. So you basically can, the compute unit can deal with 64 threads at a time. So that's what you have in a wavefront that's passing through your compute unit. And the SIMD processor itself can deal with 8 wavefronts that are scheduled. And so across the compute unit, you have 32 wavefronts that can be in play at once. Now, important point, all the threads in a wavefront are executing the same instruction, but using different data items. So in total, what you can have then, if you're thinking of your 64 threads per wavefront, and you know that you can have scheduled on a single compute unit, you can have 32 of those wavefronts, and then there's 104 compute units on the GPU. In total, that comes up to something over 200,000 threads that can be scheduled that are running on the GPU. So that's a lot of potential parallelism, and it's worth comparing with what you can achieve on the ARCHER2 compute node. So that is, you have 2 CPU processors that provide 128 cores. There's hyper-threading enabled, so you can have 256 threads scheduled to run across your compute node, and that is very much smaller than the 200,000 that you can have on a single GPU. And bear in mind that on ARCHER2 you would typically have, say, 4 GPUs or maybe as many as 8 that are attached to the same host. And when we talk about occupancy, then it's a ratio between the number of threads assigned to a GPU and the theoretical maximum number that could have been scheduled. And having this amount of level of, having this many wavefronts that are scheduled to run is useful, because a particular wavefront may be stalled. It may have to wait for data to become available, and so the GPU can switch to another wavefront that can run because the data it needs is available. And in this way, you hide the latency associated with loading the memory, loading the data that's required for the stored wavefront, because you're still allowing, you've got plenty of choices as regards which wavefront could be executing. And so you need a certain amount of occupancy, you need a certain amount of wavefronts that are ready to go to hide any potential latency that might arise. But if you have now higher occupancy doesn't necessarily mean you get higher performance. It really does come down to what your wavefronts are doing and how much memory they need. If they're needing too much memory, then you may get thrashing in the cache on the GPU, and so you may start to get slow performance if your occupancy is too high. If you're finding that your threads are trying to do too much work, too much for what the available memory supports. So the occupancy then is limited by things like the team size, the number of threads you have running per team, and the number of teams, the amount of shared memory that's dedicated to one particular team, and then the number of registers that are available for each team. And the register is like the lowest form of memory in that it's the fastest to access, and it's that memory, the registers, that the threads will take their data from. So if you had a team scheduled to run on a single compute unit, you can have up to 32 wavefronts, so that's just over 2,000 threads. Now, if your team size is 17 wavefronts, then that means you can only fit one team at a time on a single compute unit. Whereas you could have had 32. But if you try to put 2 teams, then you obviously exceed the number of wavefronts. It's 34 that you can have on that compute unit. So the possible occupancy then basically works out at a little over 50%. So it might be worth, if you're in this situation, to refactor your code to see if you could reduce that wavefront by 1, and then you'll be running at 100% occupancy potentially. And assuming that the threads in the front aren't needing too much memory, then you should get good performance there, or at least better performance than when you had 17 wavefronts per team. Now, when you schedule work, when you're offloading a loop, say, you can specify an upper limit to the number of teams that you want to use, the number of compute units that you want to use on the GPU, and then for each team, you can also specify a thread limit. And you may want to do this if you're aware of that, the work that your threads are doing requires a certain amount of memory, so you don't want the thread count to get too large. Now, with these sorts of variables that you can specify, there's variable support, sorry, since you use the word variable again, but the support for those things like num_teams and thread_lim may vary from compiler to compiler. So again, compile in verbose mode, and then also profile your code afterwards when it runs on the GPU to check what actually is going on, to make sure those upper limits that you've specified are being respected. So in general, you have to make sure there's enough parallelism to fill the GPU, and you may find that it's good to merge the small loops into larger loops. So there's enough work, then maybe the iterations will increase, and there's enough work to schedule to fill all of the compute units on the device. If you have nested loops, you might want to collapse them. So essentially you're combining the inner loops with the outer loops, and then you're increasing the number of iterations that take place. So each iteration is like a chunk of work in effect. So you've got more then to distribute over the resources provided by your GPU. Now, when you do this, and if you're able to occupy all of the compute units, you may then run into another problem in that each team is trying to do too much work, and there aren't a number of registers to support the data, the input data and the output data that's required for those threads or those teams to complete their computations. So we have a finite number of registers per compute units, and that can then also limit well, it can also limit the number of threads within a team that can be executed, or if you are running more than one team on a single compute unit, it will limit the number of teams too. So when the GPU runtime finds that there aren't sufficient registers to serve the data needs of your threads, it will do what's known as spilling the registers, in that the data that was going to be stored there can't be, so now it's going to be stored in memory that's shared by the compute unit, or shared by all threads running on the compute unit, or it may spill it further up into the global memory. But the further up it goes, I mean, the larger the memory capacity, but the longer it takes to access that memory and get it back so that it's ready to be picked up by a thread to do some computation. So to give you some details about what the registers look like, on the MI210 you have what are known as vector registers, and they will hold items or data that are specific to each thread. And so you have 64 items, 4 bytes wide. You have up to 16 registers per SIMD processor. So you basically have 4,000 bytes per SIMD, and so you have 16,000 bytes that you can be stored there per compute unit. So your vector registers, as I said, they hold values that are specific to the threads within a wavefront, whereas the scalar registers, they will hold values that are shared by all the threads in a wavefront. Sorry. So if your wavefront needs 128 vector registers, I'm just saying this doesn't look quite right. So if I've got 16 registers per SIMD processor, that's not quite right there. So I'm going to have to change the numbers here on the fly. But if you have your wavefront and it needed something like 8 vector registers, and you only got 16, then you can run 4 wavefronts can reside on the SIMD at the same time. So only 8 out of a possible 16 rather than 16 out of a possible. Yeah, I think I've just confused things here. I'm sorry, I've just got the numbers wrong. But what this is trying to say is basically if your wavefront needs a certain number of registers and you've got, let's say, a maximum of 512, let's say we're talking about a different GPU, not the MI210, but then you can have as many as 4 wavefronts that can reside on a SIMD at the same time. And if you've got 4 SIMDs per compute unit, then that means you can have 16. So the occupancy is 50% here. So apologies for that. The numbers here didn't match up with what's on the previous slide, but the concept is the same. The concept that we're trying to get across is that you have an occupancy not just on how many compute units you can use, but how many wavefronts can be supported by the available number of vector registers that are on the compute unit. So the ways that you can ease register pressure is you can, well, you can, it looks like here that you're taking the opposite tack what we did when we wanted to make sure that we had enough work to distribute all of the compute units. You can split a big loop into smaller loops, so that those smaller loops will require fewer registers, and so then they can run on the SIMD processors. But then that may introduce a bit of overhead because you may need to decrease the amount of parallelism because you're having to transmit values from one loop to the other. You can also, as I mentioned before, you can use a thread limit clause to help the compiler know how many registers are going to use at runtime, and then it may take steps. It may write the PTX code, which is when you compile an OpenMP offload region, it gets compiled into PTX, which is like a GPU assembly code, and it can take steps there to make sure that the data is organized within memory, not just within the local data store, but not just within the registers, but within the local data store, so that the memory is there to be used as it's needed, because it understands it knows how many threads are going to be in play. So there's shared memory that is accessible to all the threads in a team. So on the MI210, we have about 64 kilobytes of shared memory. So if your team requires 32, you can fit 2 teams on a single compute unit. Again, OpenMP implementations have limited support for shared memory. Make sure you compile with verbose mode, read your compiler manual, and you may be able to do some profiling also to check what's actually happening under the hood. So that's the end of that section. Apologies for the mismatch between 2 slides, but I hope it was still clear. Does anyone have any questions about that work? Okay, I'll move on to branching, which is something you don't want to do. So we're talking about code that's offloaded to the device. So your threads are grouped into wavefronts in AMD terminology. They're called warps in NVIDIA, in the NVIDIA world. And you have 32 threads per warp and not the 64 that you have per wavefront for AMD. So, all the threads in the wavefront are executing the same instruction. And if you have a situation like this, where your loop body is actually doing different operations depending on the value of the index. So here we're distributing this loop such that if your index is 0 or an even number, then you assign A to the array element. And if it's an odd index, you assign B to the array element. And what actually happens now is that there's going to be 2 threads that need to run to do these assignments. One for the even index values and one for the odd index values. And what actually happens is that each of those threads are going to run over all of the index values, actually, not just, say, for the case of A, not just the even ones, the even index positions. But when it comes to a position that it knows is an odd index value, it just masks it. In other words, it doesn't do anything. So up at the top, you can see this is what's basically happening for the assignment of A. And then for the assignment of B, you're doing the same thing, but now you're masking those array elements that have an even index value, but that's already been set to A, so that's okay. So you're running 2 instructions per thread instead of 1 instruction per thread. So it'd be really worth thinking about refactoring your code so that you didn't have any branching, because otherwise you are going to get a hit with performance. And you might have a situation that's even more extreme, but you may have like a Monte Carlo code. And so you may have a particle that's assigned to a thread, and what happens to that particle is quite random. So you would have threads doing different computations entirely. And in that case, when you're in that situation, you're going to find that your threads aren't going to be running as part of a wavefront, they're going to be running serially. So you're going to get very slow performance there. So you have to think about what actually are candidates within your code, what parts of it are candidates for being offloaded, and it may be necessary to refactor your code such that it is worthwhile offloading. So yeah, those are just the points I've just made. So that's the end of this section. That's quite a quick one. We'll now get on to memory optimization. So within the memory on the GPU, you have a structure. You have global memory, which tends to be tens of gigabytes, or maybe over 100 gigabytes for the very latest versions of GPUs that are on the market. But then within that, at a lower level, you may have an L2 cache, and I think on the AMD 210, you have an L2 cache that's accessible to all of the compute units, all of the threads running across all of the compute units. And then you have a level 1 cache or shared memory that is local to each compute unit. So each layer is faster than the one above, with global memory being at the top. So this gives you an idea of the capacity, what you can expect. So global memory can be as high as 100 gigabytes, and the level 2 cache, it may be organized such that you have different level 2, you have more than one level 2 cache, and the level 2 cache has been shared by a subset of the compute units that are on the same GPU. And that's level 2 caches of the order of megabytes, and then we get down to level 1 cache, shared memory, you're talking about kilobytes. So you're coming down by orders of magnitude, by 3 orders of magnitude each time. So when the data needs to be accessed on the GPU, when it's mapped from the host, it will be in global memory, and then it will, when it's needed, it will need to migrate down to the various levels until it's in the registers, and then it can be picked up by the thread. And then you want to organize your memory so that adjacent threads in a wavefront are accessing data that is close together in memory. So when data is being moved between these different levels of memory, is what's known as a cache line. So for the MI210, the cache line contains 64 bytes. So that's the amount of data that's being moved by a single memory load. So it's the amount of data that you can fit on a single cache line. So if you're in a situation, you know that there are 64 threads in a wavefront. So if, I don't know, if you had the situation where each thread only needed 1 byte of data, you could serve the needs of the entire wavefront with 1 cache line memory load operation. Well, that wouldn't usually be the case. So you the aim here is to reduce the amount of data traffic that's happening between layers. When you're doing memory loads, when you're transferring, say, data from the level 2 cache to level 1 cache, you're not just taking data required by a single thread, but you're taking data that's needed by multiple threads. Even if they're not running at the time, that data is in fast memory, then it takes less time for that thread, for those threads to start to run. So here's, I'm going to go through an example of what's known as coalesced memory access. So we've got our loop that's been offloaded, and we know that if you're accessing data that's at position I, it's going to be next to the data in memory that's at position I plus 1. And so we have this kind of situation. So we assume the elements in these array are doubles, so 8 bytes. So when we have the first thread that's doing the first assignment, it needs to read in 8 bytes from the cache line. So these are the arrows that you can see here, the going from 0, 1 to 6 to 7. So that's provided enough data there to allow the first thread to do its assignment, a single double value. Because the cache line has 64 bytes, we can actually then support 8 assignments in this way. So we can support 8. So we can support sort of 8 threads within the wavefront. So when we have 8 load instructions in total, because 8 times 8 is 64, so those are the threads within a wavefront, you can see that for each wavefront to proceed, we need to transfer about 512 bytes of data. And so this is an example that's quite efficient. So all of this memory access is like coalesced, because the next bit of data in memory serves the next byte in the double that's been assigned, and then when we move on, the next bit of data is the value that is required by the next assignment that's handled by the next thread, the next 8-byte value. But if we're doing something different, if when we were going around our loop we had something like a strided access, and we were moving in, we're doing a stride of 8, say, so what then ends up, the situation that you now have is that you have to do far more load instructions, because for each thread in this wavefront in green, it's going to have to read the memory on one cache line and then skip 8 bytes or so to get to the next assignment. And so what that means is now you would have to do 64 load instructions per wavefront to get the data from B. And that 64 times 64, that means it's now 4,000 or so bytes that are being transferred. So having that strided access has increased the amount of bytes that need to be moved around in memory. And so really it's very important to make sure that when you're accessing the memory, to make sure that those memory accesses are coalesced. Now, if you had a 2-dimensional array, and you then have to worry about how the data for that array is organized in memory, which indexes are contiguous, in other words. So for C, I think we have row major, so J, an element at position in J is next to the element at position J plus 1 if I remains the same value. For Fortran, it's the other way around, so we would have J indexed in the outer loop. So this is how we would need to organize things, just to make sure that when data is accessed by the threads, it's accessing coalesced memory. If you did it the other way around, so for this C example, you would, so this is showing that it would be accessed because J is on the inner loop, and we're iterating over J, which is the rightmost index. So this should be okay. It will be likely to be scheduled on the same wavefront. But if we did it the other way around, we'd have strided access between iterations of index I and I+1. So this would work less efficiently. Notice we've got the collapse keyword here to make basically to just collapse this loop into one. And similarly for Fortran, it's the same thing. It's just the other way around. So here, when we have it like this, it's coalesced, and then when we have I as the outer index, it's not coalesced. So we'd get a memory access performance hit there. So are there any questions about that part? No? Okay. I'll go on to the final part of the talk. So just these miscellaneous items. We talked about latency, latency to do with mapping data from device to GPU. There's also latency associated with launching a kernel, making sure that the parameters a kernel needs are on the GPU, and so that kernel can execute. And typically, it's of the order of around about 10 microseconds. So that's something to think about. So what you think about is that the work that's run, the computation that's been done by the kernel, make sure that it's sufficiently meaty, that it takes a sufficient amount of time, that it's large compared to the time it took to launch a kernel in the first place. So make sure that you're hiding the latency associated with the kernel launch. It may be that to get to work towards this, you need to merge small computational kernels into a larger one, so that you're offsetting against the cost of getting that kernel ready to run in the first place. So moving data between CPU and GPU is slow because typically you're using a PCIe bus, the bandwidth for which will be tens of gigabytes per second, and you have a latency in the microseconds. Whereas with memory on the GPU or memory on the host, latency is in the nanosecond range and bandwidth is hundreds of gigabytes. So you want to avoid, want to restrict, minimize the number of times you're doing that CPU to GPU transfer. So you can have these constructs, enter data and exit data, where if you're offloading the same loop multiple times during the running of your code, and you know that certain of the input arrays that are used by that loop, some of them don't change in between loop invocations. In fact, they're initialized once when the code starts, and they never change during the lifetime of the code. So you wouldn't want to be mapping the data in those arrays every time you offload that loop. So what you can do for those data items that don't change, you can use this enter data, exit data construct. So you can imagine if you had in your main file within your code, you would have a pair of these that would surround the main body of your code, and then within the body you're calling functions that are defined in other compilation units or the source files that call functions, and then actually offload a loop that maybe use the arrays that were offloaded or mapped via the enter data clause. Your GPU runtime would know that those arrays already exist, so it wouldn't do the same thing again every time you call that loop. So that's a way of minimizing the number of times you transfer data over a slow PCIe bus. If it is a place that every so often, it may be that one of the input parameters to a kernel, or it changes, the data changes, you can do make an update call just to update the new data such that it is on the GPU. If you want to allocate data on the device, you can make sure you use the alloc clause to make sure that it is allocated on the device, not allocated on the host, and then whatever initial values are then mapped to the device. You can do that the alloc clause to make sure that it's confined to your GPU, the allocation. You can try things like using the first private clause for scalar data. So then the compiler would pass that in as an argument to a kernel rather than trying to map it separately. And also, if you're doing some linear algebra for which there is an implementation in a library that could, that supports running on a GPU, then make use of that library, because that library is likely to be tested a lot and is likely to work correctly and to be to be highly performant. So there are vendor independent ones such as Magma, but there are also ones for particular hardware platforms, and I mentioned these already, the ROCm libraries and the NVIDIA SDK libraries like QBLAS. And then when you're using those libraries, I think this is something I mentioned at the start of the previous talk, when you're using those libraries, you may need to, within OpenMP, make sure you're using isDevicePointer or hasDeviceAddress to make sure that your OpenMP runtime knows that these pointers are pointed to data that's already on the GPU. And finally, and there's also asynchronous tasks, which you can do to make sure that the host is occupied with work all the time, and also you could schedule multiple kernels onto the GPU, hardware resources allowing. So this is just making sure that there's nothing idle either on the host or on the GPU. This is what asynchronous tasks allow you to do. And finally, when you do OpenMP directives like this and you have your construct with various keywords after it, there is a certain amount of overhead associated with each of those OpenMP directive lines. And so if you can minimize the lines, that reduces the overhead slightly, I think. So here's an example here where you've basically combined two OpenMP directives. But it's your choice. It may be when you split things up like this that it makes your code easy to understand. But there is a saving potentially that you could be made by reducing the number of OpenMP directives that you have in your code. I think, and that's just saying the same thing, but for Fortran. So to conclude, you have to ensure that there's enough parallelism to fill all the compute units. So you have enough iterations in your loop that can be distributed over all of the SIMD units that you have in the entire GPU. Avoid branching, because it means that you end up doing unnecessary work, or each thread spends half of its time potentially doing unnecessary work. Optimize memory accesses to make sure that neighboring threads within a wavefront are accessing data elements that are adjacent in memory. And there's this tension here, although you need to make sure that there's enough work to distribute over all the compute units, within each compute unit, you need to make sure that there's not too much work that you're running out of registers. And so that would cause register spilling, and then data would need to be moved out to the local data store, or it may be even global memory. So that just means that your threads would take longer to run. So you try and, within a compute unit, tailor your workload such that it's consistent with the number of registers available. So that finishes that section and the talk overall. Does anyone have any questions? Okay.
So can I ask something?
Yeah.
Okay. So I just have questions for the last item. How can we guarantee the kernel is simple enough? I don't understand this one.
So what's really useful here is when you use, say if you're running on a NVIDIA GPU, to basically profile your code afterwards. There's things like Nsight systems, which will give you an overall picture. So it will tell you which kernels account for much of the runtime. When you want to get things that register pressure, you need to know you need to use something called Nsight Compute. So it's another tool. So there are equivalent tools with the AMD software suite. But just to give NVIDIA as an example, that will then, for specific kernels that you specify, will tell you what the register occupancy is. So it will tell you if registers are being spilled, or if the kernel that you're trying to run needs too many registers than there are available. It also may say the opposite finding, that it may say that half of the registers are not in use here. So
okay. Can I understand this like so if my kernel or my function is quite complex, should I divide this functions into different kernels, and to feed the GPU into different steps?
Yeah, I would do that at first. I would start just to experiment with a simplified version of your code, and then to build it up, and then you get an idea of how the performance is, and then which part of your code is the one that causes a performance issue.
Okay.
So there's a question from Ian. Is there a way to make use of graph-based kernel launches in OpenMP? I'm not sure. So I only know of that with CUDA. So I don't know if it's possible. I need to check that. I have to get back to you about that. But I do know about CUDA graphs and that, and where if you had the same set of kernels being launched all at the same time, you instead would record that and launch the graph instead. So I don't know if there's interoperability with OpenMP as regards CUDA graphs. I'll check.
Okay.
Thanks. Okay. And from Jacob, for things like Monte Carlo codes, is branching unavoidable? Are there tricks of the trade that you could point me at for further reading? I don't know for Monte Carlo codes. I don't know if you would do separate kernels for each branch. You may take that approach. So you may need to do something up front where you kind of have a certain number of iterations, and there's branching inside the loop, and there's some way of working out how many iterations will apply to one branch, and how many would apply to the other, and then organize your kernels appropriately. So that's the only thing I could say for that one.
Okay, thank you.
I did have a response to a question asked earlier about mapper declaration. And I was just speaking to a colleague at EPCC, who was on the standards board for OpenMP, and he thinks that for custom mappers, they have to be in the same scope as when you use it. So that it does have to be in the same scope. I think that's a question that Ian asked. So that is unlike the other constructs you can use that I talked about, the enter data and the exit data ones. Are there any other questions anyone has? Okay, that's great. Well, thanks for listening. Goodbye. Enjoy the rest of your day, and I don't know if there's anything left of the course, if you have any more programming exercises, but that's great. Hope to see you at other EPCC courses in the future. Goodbye, everyone.